Hi guys, let us start this course Digital Logic Design with logic gates. So what is meant by a logic gate? Logic gate is a building block of the circuit. So basically we have three logic gates, basic logic gates, which are AND or NOT. Okay, so let us write them first. So the topic is logic gates. So we have basic logic gates, and those are AND gate, OR gate, NOT gate. Okay, so you can note it down like this, like bullet points. And in this course we will be looking at the truth table and circuit diagram of this AND or NOT gates. Okay, so let us see them first. So AND gate is represented as like this, and OR gate is OR gate is represented as this, and NOT gate is this. Okay, AND or NOT. So let us see the truth table of AND first. Okay, so before entering into truth table, let us have some basics here. So this is a signal, A signal, this is B, and this will be A and B. Okay, so in the logic sense, dot means AND. Okay, so this is a signal which is labeled as A, and this is a signal which is labeled as B, and output will be A plus B. So logically, plus, I mean in this context, plus means OR. Okay, so if for this NOT gate, if you provide A as input, A bar will be the output. So what do I mean by A bar is, if 0 is provided, 1 will be the output. If 1 is provided, 0 will be the output. Okay, and one more thing, sometimes 0 and 1 is referred as low and high, 0 as low, 1 as high. Okay, so both of them got same meaning. Either 0 or low is same, either 1 or high is same. Okay, so let us see the truth table. Okay, so we have two inputs. Okay, remember, if this is a signal which can be either 0 or 1, and this is another signal which can be either 0 or 1. Okay, so here we have taken two input AND gate, so it can be 3 input or 4 input or n input. Okay, but the output will be only one signal, either it can be 0 or 1, but not both at the same time. Okay, so same applies to this OR gate as well. So we can have 2 input or 3 input or n input OR gate, but the output will be only one signal. It can be 0 or 1, depends upon the values of these signals. Okay, so about this one you know already. So whatever the input is, you just complement it. So the complement is represented as this bar. So let us write the truth table for A and B. So this is A, this is B, and this is A and B. Okay, for A and B, so what are the possible values of the signals? So A can be 0 and B can be 0, that is one possibility, and A can be 0 and B can be 1, that is one possibility, and A can be 1, B can be 0, that is one possibility, and A can be 1 and B can be 1, that is one possibility. Okay, so here A and B will be 1 only when A is 1 and B is 1. In the rest of the cases it will be 0. That is AND gate. Okay, so see here once again, A and B will be 1 only when A is 1 and B is 1. In rest of the cases it will be 0. Or else you can say in terms of low and high as well. A and B will be high only when A is high and B is high. In the rest of the cases it will be 0. Okay, so Let us write the truth table for A or B. Okay. So actually I have to write the separate truth table for A or B, but I have just combined them. A or B will be 0 only when A is 0 and B is 0. In rest of the cases it will be 1. Okay. So this is entirely contrast to this one. See, A and B will be 1 only when A is 1 and B is 1. In rest of the cases it will be 0, but A or B will be 0 only when A is 0 and B is 0. In rest of the cases it will be 1. That means for A or B to be 1, it requires only single one. Here there is one, here there is one, here there is one. So output is 1. Okay. So we have to focus on this one and this one. Okay. In the textbooks as well, they used to represent that A and B will be 1 only when A is 1 and B is 1. And for the OR gate, they will be representing like this. A or B will be 0 only when A is 0 and B is 0. Because the rest of the cases are more. That is why they are not telling you in terms of these cases. This is the only odd one. That is why they are telling in terms of these cases. Okay. So final thing is you have to understand that A and B will be 1 only when A is 1 and B is 1. In rest of the cases it will be 0. Or you can understand in this way. If at least 1 0 occurs, then output will be 0 for A and B. Okay. Here there is 0, here there is 0, here there is 0. That is why output is 0. And the rest case is 1 and 1. For that input A and B will be 1. Okay. So in the case of A or B, it is different. If at least single one is available, then output will be 1. See here. So we have 1 here, here and here. So that is why we got 1 for these cases. Okay. So if both of them are zeros, only then A or B will be 0. Okay. That is how you remember. So this is obvious that when you give 0, it will give you 1. When you provide 1, it will give you 0. So now let us see the circuit diagram. These are two switches A and B. So see here, A and B. For if A is on and B is on, only then output will be 1. In this case, bulb will glow. That is the meaning. Okay. So if this is on and this is on, then the current flows, bulb glows, output will be 1. So if A is off, so we have seen this case, first case we have seen. So let us start with this case. A is 0 and B is 0. That means A is off and B is off. Then the current will not flow, then the output will be 0. So when A is off and B is on, A is off, B is on. Okay. So B is on. Then the current cannot flow through this wire, so output will be 0. Now A is on, B is off. A is on, B is off. Okay. So same problem. Current cannot flow, bulb will not glow, output will be 0. So only in this case, bulb will glow. That means the output is 1. So in case of OR, the circuit diagram will change slightly. Okay. Sorry. Okay. This is a B switch. Okay. So for A is off and B is off. So this is off, this is off. So there is no way to enter the current So output will be 0. So A is 0 and B is 1. So A is 0 in the sense A is off and B is on. So current can flow through this wire and reach the bulb, so output will be 1. And in this case as well, A is 1 in the sense A is on. A is on and B is off. Okay, so current can flow through this wire and reach the bulb, so output will be 1. So this case is both of them were on, so current can reach this bulb, output will be 1. This is the circuit diagram of A or B, and previously we have seen A and B as well. Okay, let us represent this notation in the Venn diagrams as well. Okay, I think you have an idea on sets. Okay, so universal set, in that set you have two sets. Okay, so A and B, this is A and this is B. Okay, so A and B can be represented as this. Okay, A and B can also be represented as A intersection B, because here the condition is if A is 1 and B is 1, then this will be 1, right? I mean the output is 1. And here also the condition is A should be present and B should be present. That is why A into B will be equivalent to A intersection B. And the next one, OR gate. OR gate can be represented like this. Okay, so that means this part and this intersection part and this one also comes under A or B. Okay, here A union B will be equivalent to A plus B. Okay, or A or B, not plus B. Okay, so then how can we represent NOT gate? Let us suppose this is a universal set, this is set A. Okay, so NOT gate can be represented as this one. That means the NOT gate will be except A, I mean outside A, because NOT gate is that if you give A, it will be A complement, right? So that is why we are shading the outside region of A. Okay, so this is regarding the Venn diagram representation of these gates. Okay, so in the next video we'll be looking at the NAND, NOR, XOR, XNOR gates. Okay, thank you.